Chapter 2, Section 1. Now we are on Part C, and we're going to talk about velocity and speed. So, velocity, okay? How far an object travels, its distance or displacement, okay? Where it stops, where it starts. That's not the whole story of motion. How quickly an object moves from one position to another tells us another thing about motion. And we call this, okay, average velocity. And we write it as V, average. And realistically, we'll often just change this and just write V and assume we're talking about the average velocity, okay? So velocity tells us how quickly an object moves from one position to another. And we can calculate it using this equation, where the average velocity is equal to the displacement divided by the change in time. Please note that this is displacement and not distance. So let's look at an example. We have got a cat here, okay, and he is going to be traveling a displacement of 10 meters. So, in the first situation, A, his time, he travels that whole distance in 2 seconds because he's chasing this little mouse here. Okay. So when we calculate that, then we have our equation, right? V equals delta x divided by delta t. So we're going to take that and plug in our numbers. Delta x is 10 meters divided by our time of 2 seconds. So the total velocity is 5 meters per second. Velocity does not have its own separate unit. It just uses the base units of meters and seconds. Okay, so it tells you how far in what time. So you went pretty fast that time. 5 meters per second is really fast. Now the cat's not chasing anything. So he just walks slowly along, and now it takes him 5 seconds to come up. So plugging that again into our equation, we still have 10 meters for our displacement. So now it takes him 5 seconds to travel that. And we get that the cat travels at 2 meters. All right, so that was some really basic examples of calculating average velocity. And again, in a math video, we'll do a few more examples if you still have questions about how to calculate that. So here's why I wanted you to notice that it's displacement and not distance. Because velocity and speed are not, let me repeat that, not the same things. Okay. But in everyday language, we use them similarly, and we often use them interchangeably, meaning we'll say velocity or say speed, and we don't care which one we say. But in science, they mean two very different things. So, in science, velocity has 2 parts to it: magnitude, okay, and direction. So magnitude, if we went back to the cat example, would just be the values of 5 meters per second or 10 meters per second. Okay. And velocity is always displacement over time. So if we really wanted to be extremely accurate, we would need to say that the cat traveled 5 meters per second to the right or to the left or whatever direction we chose. Okay? But the magnitude part of the equation is just this number, okay? And sometimes we refer to the magnitude of velocity as the speed of a velocity. But velocity has direction, okay? Speed just has magnitude. So it's actually the distance traveled divided by the total time, not the displacement. And as we showed you earlier, you could have a distance that is completely different than the displacement. And so you would get 2 different values if you calculated that. One other thing we need to look at is something called instantaneous velocity. Okay, and the root word here, if it helps you remember, is instant, right? An instant in time means just that like one moment. And this can be a very different thing than average velocity sometimes. So to understand this though, we're going to talk about speed because it's a little bit easier, but remember with velocity we would include direction. So I want you to think about driving a car, okay? You're in your car, and that's a weird little car going down the road here, okay? And when you drive your car, you don't drive at the same velocity all the time, right? You speed up, you slow down, you stop at stoplights or stop signs or because someone cuts you off, and eventually you get to where you're going, and you even stop then. But all that time you're speeding up, you're slowing down, okay? You might stop for a second before you go and stop again. Okay, you even change direction. So all of this is happening. So, at each moment while in the car, you can look at your speedometer, and that's the thing that looks like this here, okay, and see the magnitude of your velocity at any time. This magnitude that you're seeing, and gosh, I hope you're not going that fast, okay, that is your instantaneous velocity, or really your instantaneous speed, but if you know what direction you're going, then you could say what your velocity is as well. So your instantaneous velocity is just your velocity at an instant in time. We can use graphs now to visually interpret velocity, which means understand what's happening. So here's a really basic graph, and it's pretty good except they forgot to include time, so maybe this is time in minutes. It could be time in seconds. I'm going to say minutes. Okay. So in this graph, what we have happening is we have the distance here on the x-axis and time on the y-axis, and we have the graph of the motion. I want you to notice that in velocity graphs, they always have position, or the distance, it could be displacement also, on the y-axis. That's all the time. It's never going to change. And time is on the x-axis down here. Okay, you can see it right there at the bottom of the screen. So, I want you to notice that in fact, all physics graphs and every single one, time will always be on the x-axis. So it doesn't matter if we're graphing velocity, acceleration, or anything. Anything we compare it to time, time is right down here on the x-axis. No exceptions. So let's look about how to interpret this a little bit more. Okay. So one of the things that we can interpret is what the slope of the graph means, because the slope can change. Okay. And it turns out that when you have a distance versus time graph, the slope is equal to the velocity. So we can calculate the slope using our good old algebra equation, rise over run. And since slope is equal to velocity, that means our velocity is equal to rise over run. So if we calculate it real fast for what the velocity is between point A and B on this graph, maybe this is a car traveling down the road, okay? Point A here is at 1, 0.5, and B is at 2, 3.2. Then to calculate this, we've just got to plug it in. Our rise, remember, is the difference between our y values. Okay, and sorry I drew that a little wrong. Y is over here. So we're going to have our second number minus our first number. And then we have our time values on their x-axis, so that is our run, and we're just going to have 2 minus 1. So 2 minus 1 is equal to 1. 3.2 minus 5 is 2.7 divided by 1 equals 2.7. Okay, so our velocity, I ran out of room here on the screen, but our velocity between A to B, okay, so I might write that velocity of A to B is equal to 2.7 meters per second. And you can always find the velocity like that by using the slope. The last thing I want to point out here is kind of what the different shapes of graphs might mean, okay? So again, we have our distance and time graph, okay? With this, the slope still is equal to our velocity. So thinking about that, if we have a really steep slope, okay, we're going to have a very fast speed. Okay, and when it says steady, it means not changing. So anytime you have a straight line, you have a constant velocity. Okay. The red line here, okay, we've got a constant velocity. It's a little slower now than the green line. But when the flattens out, it's got a slope of 0, so it has a velocity equal to 0. So it's stationary, which means it's not moving, okay? So the distance isn't changing with time, so there's no motion. Okay, and then it returns to where it started. Because this is distance, okay, it's wherever it started, and it's coming back. So this is literally kind of the path traveled, except we have time here, so it probably just stayed and then came back. The last one in blue here, okay, there the slope is changing, right? It's not a straight line, okay, and we'd actually need calculus to calculate that. But it just means it's getting faster in this case. Okay, so the velocity is changing. The velocity might be, 0.5 meters per second here, and then somewhere in here it's a 1 meter per second, and then it gets even faster, maybe it's 3 meters per second, but it is changing. We'll look a little bit more and have more practice with graphs and interpreting them in class.